Welcome back to AI.Code.Cast, where we dive deep into fascinating coding challenges.
Yeah.
And today we're going to be tackling one that sounds a little bit whimsical,
Yeah.
but it's actually surprisingly relevant.
Yeah.
It's called rotting oranges.
Rotting oranges. It's a classic problem, actually.
Oh, really?
It's one of those ones that you see pretty often, and it's a great way to sort of illustrate how even a seemingly whimsical scenario can actually teach you a lot about algorithms
Right.
and about efficient problem solving.
Okay, so imagine you have a grid.
Okay.
It's kind of like a crate of oranges, right?
Mm-hmm.
And some of them are fresh.
Yeah.
Some of them are rotten.
Uh-huh.
And there are even some empty spaces.
Right. Well,
And the rotten oranges, they're kind of contagious.
yes.
So over time, they turn the oranges that are next to them rotten.
Exactly. So the challenge is to figure out
Okay.
what's the minimum amount of time that it would take for all the fresh oranges to rot, assuming that it's even possible.
Right.
Because some of them might be completely isolated,
Right.
and they'll never succumb to the rotten influence.
I got it.
Mm-hmm.
So it's kind of like a race against time.
Yes.
But instead of runners, we have rotten oranges spreading their,
Right.
well, rottenness.
Their rottenness, exactly. And we have to figure out what's the fastest way for that rot to take over the entire grid.
Precisely.
Mm-hmm.
Now, before we dive into like the best way to solve this,
Sure.
let's think about
Yeah.
a more brute force approach.
Okay.
Could we just sort of
Yeah.
simulate the rotting process step by step and just see how long it takes?
That's a natural first thought.
Right.
I think a lot of people would think that way.
It seems pretty straightforward.
Yeah. And
Yeah.
it seems pretty straightforward.
Keep track of which oranges are rotten at each, point in time and update the grid accordingly.
Right. Hmm.
What's wrong with that approach?
So it might work
Okay.
for smaller grids,
Mm-hmm.
but it quickly becomes inefficient.
Okay.
When you start dealing with larger grids.
Right.
Imagine a massive grid with hundreds or even thousands of oranges.
Yeah.
Simulating every single step would be really computationally expensive. And even then, it might not even guarantee that you found the absolute most efficient solution.
Ah, I see.
Yeah.
So we need like a more strategic approach.
We need to be a little bit more clever about it.
Right.
Yeah.
And I see here that our outline mentions
Okay.
breadth first search, or BFS.
Yes.
Is that our algorithmic savior here?
It is. BFS is a great way to solve this problem.
Okay.
It's a graph traversal algorithm that systematically explores the grid, level by level, starting from the initially rotten oranges.
Okay.
Think of it almost as a wave of rot spreading outward.
Okay, so I'm starting to get the visual here.
Yeah.
But how does BFS actually help us define that minimum time?
So the key here is that each level of that BFS exploration represents one unit of time. So as the algorithm explores the grid, it's keeping track of the time that it took to reach each fresh orange.
Okay.
And by the end, we know the absolute earliest that each orange could have been infected.
Interesting. So BFS makes sure that we're always considering the shortest path for that rot to spread.
It guarantees you're going to find the shortest path.
I like it.
Mm-hmm.
Before we get into the actual specifics of how BFS works,
Sure.
Can you clarify something for me?
Yeah, absolutely.
What happens if a fresh orange has multiple rotten neighbors?
Okay.
Does it get infected multiple times?
That's a great question.
Right.
And it's a common point of confusion.
Yeah.
Once an orange is rotten, it stays rotten.
Okay.
We only care about the first time that it was infected because that determines the minimum time for the rot to actually reach it.
That makes sense.
Right.
We're not concerned with redundant infection.
Yes.
We just want to know, like, the fastest way for the rot to spread.
Exactly.
So how does this BFS algorithm actually work in practice? All right, so let's break down BFS.
Okay.
It sounds like there's a queue involved.
You are right on the money. A queue is a key part of this.
Okay.
We start by creating a queue and adding all of the initially rotten oranges to it.
Okay.
So think of this queue as a line of oranges waiting to spread their rottenness.
Okay, so they're first in line
Yes.
to infect their neighbors.
Yes.
Then what?
Then we go through that queue, one orange at a time.
Okay.
For each rotten orange, we check its 4 immediate neighbors.
Okay.
Up, down, left, and right.
Right.
If a neighbor is fresh, we mark it as rotten since it's been infected, and then we add it to the back of the queue.
Got it.
So it can eventually infect its own neighbors.
Right.
And very importantly, we record the time it took for the rot to reach that newly rotten orange.
So keeping track of each generation of rot, basically.
Exactly. We're keeping track of how long each generation takes.
Okay, I like that. And then...
And we repeat this process, taking a rotten orange from the queue, infecting its neighbors, adding them to the queue, recording the time until the queue is empty.
And then at that point, we've either successfully infected all the oranges, or we know that it's impossible.
Exactly.
Because there are some fresh oranges that are... Some of them might be completely isolated.
Completely isolated.
And unreachable by that wave of rot.
So BFS provides us with this systematic way to explore the grid. Making sure that we find the shortest path.
Yes, it's a very elegant approach.
Yeah, very elegant in its simplicity. I like it.
I agree, but our discussion wouldn't be complete without talking about a clever optimization in place BFS.
In place BFS, yeah.
Have you heard of this?
I've seen the term.
It sounds like we're somehow performing BFS without needing extra space.
Exactly. With in-place BFS, we can get rid of that separate queue that we were talking about and just use the grid itself.
Wait, hold on.
Yeah.
How is that even possible?
Okay, so...
The grid only tells us whether an orange is fresh, rotten, or empty.
Right.
How can it also act like a queue?
It's all about clever use of timestamps.
Okay.
So imagine we assign a timestamp to each orange directly within the grid.
Okay.
This timestamp represents the time at which the orange became rotten.
I see where you're going with this.
Yeah.
So instead of adding oranges to a queue, we just update their timestamps in the grid.
Exactly. Initially, all of the rotten oranges would have a timestamp of, say, 0. And then as we explore the grid, we increment the timestamp for each newly infected orange.
So the timestamps act as a sort of virtual queue.
Exactly.
Guiding the order of the rotting.
You got it.
The oranges with lower timestamps rot first?
Yes.
And then they spread to their neighbors, giving them a higher timestamp.
That's exactly how it works.
Brilliant.
And the beautiful thing is we're not using any extra space for a separate queue.
Right.
Everything is managed directly within the grid.
That's really impressive.
It is pretty neat.
Are there any downsides to using in-place BFS?
So it's a bit of a trade-off.
Okay.
While it does save space, it might actually be a little bit slower than standard BFS.
Good.
Because we have to repeatedly scan the entire grid to find oranges with a particular timestamp.
So it's that classic trade-off, space efficiency versus runtime.
Exactly.
And speaking of different approaches, one of the sources that I was looking at mentioned depth-first search, or DFS. Could we use that here too?
We could technically use DFS, but it's not as efficient as BFS for finding the minimum time. DFS tends to go down one path as far as possible before backtracking, which means it might miss a faster, more direct path elsewhere.
That makes sense.
Yeah.
We want to find that quickest way for the rot to spread.
Exactly.
And BFS seems much better suited for that.
BFS systematically explores the grid level by level, ensuring that we're always considering those shortest paths for the rot to propagate.
I'm really starting to appreciate the power of BFS in solving this.
Yeah, it's a very elegant and powerful algorithm.
It's really amazing how this problem, like rotting oranges, can illustrate the power of algorithms and you know, efficient problem-solving techniques.
It goes beyond just oranges, too. You can think about how BFS could be applied to other real-world scenarios. Like social networks or the spread of diseases.
Yeah, like in a social network, Each person could be like an orange, and the rot spreading through the network could be a piece of information or a trend or something like that.
Exactly. BFS could help us analyze how quickly information spreads, identify key influencers, understand the dynamics of social connections.
Yeah, and in the case of like a disease outbreak, BFS could help model the spread of the disease and inform strategies for like containment and stuff like that.
Exactly. It's a powerful tool for understanding and predicting the spread of anything that follows this kind of network-like structure.
This has been a really insightful deep dive into the rotting oranges problem. I feel like I have a much better understanding of, you know, the problem itself, the brute force approach and then, the elegance of BFS in finding that optimal solution.
I'm glad to hear that.
Yeah.
It's a great example of how even a seemingly simple problem can lead to a deeper understanding of algorithms and their real-world applications.
Before we wrap up, any final words of wisdom for our listeners who might be tackling this problem themselves?
I would encourage everyone to just play around with it.
Okay.
Try different grid configurations, see what happens.
Yeah.
Try implementing both the standard BFS and the in-place BFS.
Right.
And really just think about how these concepts that we've talked about today could be applied to other problems that you encounter in your work or in your studies.
Great advice.
Yeah.
Well, thanks for joining us on AI.Code.Cast.
Of course. It's been a pleasure.
We hope you enjoyed this juicy exploration of the rotting oranges problem. Until next time, happy coding.